Hi guys, welcome to the next lecture in Python programming for people that want to grow up to build aeroplanes. So in class on Wednesday, we went over through, we did a few things in Wednesday. We went through a quiz of all of the things we've covered so far, and then I gave you another quiz element, which was an introduction to the Monty Hall problem. Now, some of you guys had already been through the Monty Hall problem. Others hadn't. If you are watching this video and you either haven't gone to my lectures, then have a quick look at what the Monty Hall problem is. There's countless YouTube videos, not countless, there's a number of YouTube videos out that explain it. And in class, we sort of proved that the correct choice was always to switch, and we proved it sort of three different ways. So we looked at the statistics. So we did a choice tree and showed that actually always the best choice was to swap. We then did a sort of a counter example. So we did Reductio ad absurdum. We said, which is basically where we increase the number of doors, and we said, well, it's obviously very logically the choice to switch when there's a greater number of doors. And then lastly, I showed you a bit of Python code, which was almost a brute force approach. Okay, so I'd say it's not almost a brute force. It was a brute force approach. So it was a code that very quickly we ran up to 300,000 games and showed that the probability of winning was very, very close to 2/3. It was a number that approximated 2/3 all the time. When you switched, and it was a number that was much less. It was 1/3 if you didn't switch. So let me just bring up the piece of code that I showed you in class. So the history of this code was that online I found an example that someone else had written for a Python code that explains the Monty Hall problem. So this was the code that I showed you guys. Let's run it for 10,000 cases. So 10. So if we run 10,000 successive games of the Monty Hall problem, if I run this, it takes a while to get the kernel to start, so it's still not running the code yet. But it runs pretty quickly, and then it shows the successive probabilities of if you switch and if you stick. And annoyingly, those aren't showing up, so let me just mess around with my screen 1 second, because that's going to be important for this lecture. There we go, so that's a better look. Okay, so what we see here, we saw the probability if you stick or if you switch. So then we have along here, we've got on the x-axis of these, it isn't quite displayed, we've got successive number of games played up to 10,000. If you stick with the original choice, this is what we had here, and you see your probability is low. It's this number that's sort of very, very close to 33. And obviously that just tends towards that number the more games you play. And then we saw this number is very, very close to 66%. Okay, 2/3. This is 2/3. I think this one should be 2/3, and this one is 1/3. So this piece of code runs very, very quickly. And the reason I wrote it was because I found an online example that someone else had written. It's on the site medium.com. You can probably find it. Again, their explanation is really good for what they did, and I'm not trying to shit on what they wrote, but the code is not particularly efficient. It's not extensible for the purposes that I wanted to do, which was changing the number of games and running them very, very quickly. At least not easily implementable. And also, there's a number of different ways you can crack any problem, crack any walnut. And I'm going to go through and rewrite this code now, sort of using the same sort of methodology that I chose before. But we'll find that we're not going to end up with the exact same piece of code. So let's have a think about the different problems we need to solve. So I'm going to write this in Spider, and I'm going to narrate it as we're going through it, and we can talk about the different parts of this problem. So this is my Spider window over here. So I know there's a few packages I'm going to be using. Let's say import some packages. So always Numpy, and we're going to import. I'm trying to think, do I use random in the end or not? I don't know if I use the think I just used the random module within Numpy actually, so that should be enough. Again, we're going to also want to plot some things. So import matplotlib.plt as .pyplots as plt. So we're going to use those two. So we're going to make one user thing we can change. So the only input we want is the number of games. So what we want this code to do is go through a successive number of games and then show us how many of them you win if you switch and how many you win if you don't switch. So we'll say n, and in the first instance we'll just choose to do 10 because this means we can run this code quickly and we can effectively show what happens each time. So I'm going to make a function within this script that I've written, and it's just going to be called Monty Hall. And what this is going to do is going to be the main function that's going to run everything. So I'm going to do down here def Monty_Hall, and then the input to this is the number of games that's played. So this is the function that what it needs to do. It's got to, for n number of games, which here is set to being 10, but can change. It's got to set up a random array of which door you choose, so 1, 2, or 3. It's got to set up a random array of which one the winner is, 1, 2, or 3, and then it's got to do some logic to decide, okay, well, the host has got to choose a door that isn't the winner and also isn't your choice. So there's got to be some logic that we're going to have to do. So we're going to have to use some other sub-functions, and we'll talk a little bit about sort of logic control in this. So this script here, when I run it, this script has got access to everything that's been run before this point. So I'm going to pull def Monty Hall, and we're going to do the very first thing we need to do is make a random choice array. So I'll tell you what else I'm going to do actually. I'm going to introduce you to something that I didn't have in the original code, but I'm going to put here verbose equals to true. So there's two arguments that go into this now. N is the number of games, and then verbose is just this Boolean flag. And verbose can mean a lot of different things. In language it means it's heavy with words, but in programming it tends to mean that I'm going to say everything I do. So if I set it to be true by default in this, I could just easily change this later. What this enables me to do is it enables me to display things to screen based on the value of this Boolean array. So I'm going to say print the intro, and we'll say if verbose, so it's then just this logical array, colon, we're going to say setting up and if I run this, so it now has run. Okay, that's fine. So, and just put for the record, the way that I'm running this, I'm pressing shift and then return. So it hasn't done anything because I haven't told it to do anything. So what I can do down here now, so I've got my function defined Monty Hall, and remember everything that's indented was part of this function. I can now run this. So I can say Monty_Hall, and then the only input I want to give is n, which I've defined up here to be, let's put this down here actually. And we'll put some more narration in here. Okay, so for now, I've got my function defined, I've got the number of games I want, and then I try and actually run the Monty Hall game. Okay, so if I run this, we see I run the right-hand side. Let's just do a quick clear here. I'm going to run, I can press shift or enter, shift and enter, or I can press the play button up here. I'm going to press shift and enter. It says over here, it says setting up 10 games of the Monty Hall problem, and that's because this verbose flag was true. If I set this by default to be false and run it again, nothing happens. It doesn't print that part to screen. I'm just going to set this to be true up here. another way that we could sort of test this code, and this is just handy to be printing things to screen. I could have it be default to false up here, and then I can over on the right hand, in the Monty Hall, I can then just put a second argument into here. I can either, because it's a positional argument, I can say it's true here, and it knows that that has to be the verbose flag, or I can say verbose is equal to true. There's two different ways of doing this. Oh, no. That's auto-completing if I try and do shift and enter. There we go. So if I do shift and enter, it now says setting up 10 games of the Monty Hall Problem. So it hasn't done anything yet, so we need to actually do this. So we're going to set up an array of 10 that has the choices of the first, second, or the third door. And we remember that in Python, indexing starts at 0. So our doors are going to be door 1, 2, and 3, and those are going to correspond to the Python index 0, 1, and 2. So we want our array to be a random array of the integers 0, 1, or 2 that has 10 values. So we'll put this over here. So then this is just going to be a numpy array, and we can use the numpy.random.randint method. So we'll say player choice. I'll say it's a player playing it, np.random.rand, and you see it auto completes here. So I can now tab down to Randint, and I'll press tab again, and it auto completes it. So says I want to have the maximum it can be to be 0, 1, or 2. So I have 3 is my sort of limit on the maximum size the number can go to, and then the size is going to be equal to n. If I run this now, it runs, and it again says setting up this number of games of the Monty Hall Problem, but it doesn't actually do anything. So what we want to do here, we can have another verbose printing. So we'll say if verbose prints run this again. So this then gives the player choices. Setting up 10 games of the Monty Hall Problem. Player choices are 1, 2, 1, 2, 0, 0, 0, 0, 1, and 2. And that corresponds to doors 2, 3, 2, 3, 1, 1, 1, 1, 2, 3. If we run this again, we get different numbers. Okay, so we'd run it again, get different numbers, get different numbers, get different numbers. Everything's pretty easy. And we can, the logic of having this sort of verbose flag will become apparent once I set up, say if I put 100,000 games in, it will still print these out, but we might want to no longer, again, it's sort of truncated the values here. We can easily just set this to be false at this point down here. So let's change this. Okay, shift and enter, and it no longer prints that. But for the purpose while we're writing this code, we want to have this verbose flag on, and it will just help us understand the different parts that are available in this code. Okay, so we've made the random choice array. We now need to do the exact same thing that chooses the winning array. So we'll say winning door. And we're just going to repeat this line up here. So it won't give the same values because the way that the random method works is that it takes the value of the clock at whatever time you happen to call it, and then that provides a seed to the random number generator. So these will be 2 different doors, so 2 different sets of numbers. They might have the same value, and that just means the users picked the winning door. But we'll go here. So we'll say player choice. Let's change this to be be randomly selected. So if we run this, let's just put this down to 10 again so I'm not burning through my CPU. Okay, so it says here we've got those two choices. Player choices are doors 2, 3, 1, 3, 3, 3, 3, 3, 2, 1. That's quite difficult to do those changes in your head. And in fact, I'll tell you what, let's just do... rather than using Python indexing, let's change this. Let's change this to be... See if I can get this to work. Let's change this to be doors 1, 2, and 3 because that Python indexing just gets a little bit confusing in a game like this. Okay, see you later. Love you. Okay. So that Python indexing can get confusing in a game like this. Let's just change those indices. I could do it easily. I could just add 1 to it here. Yeah, let's be lazy and let's just do it this way. So these then give the door numbers being 1, 2, and 3. That's not the same as the code that was handed out, but this is just maybe slightly easier to understand. Hopefully this won't cause any issues later. Okay, so we've made the random choice array, we've chosen the winning array, so we can now just see, we can go through and see which one is won, but what we need to do is we need to get the host to remove a door. And this is going to be slightly more difficult to do because it's then a function of both the random choice array and the winning door. So we need to think about how to do that. So there's lots of different ways we can do this. I ended up putting this as a separate sub-function in the last one. Let's do that again. So actually, let's not do that. I'm going to write this code slightly differently. So let's think about how to do this. So we need to go through. There's probably a way to do this using some smart Boolean indexing. Let's think about this. In fact, I lied. I am going to put this as a sub-function. So we're going to call this. We're going to say host removes is equal to host choice, and it's going to be a function of the player choice and winning choice. So if we try and run this now, it'll throw an error because we haven't described this host choice function. So because it's a function that needs to be accessible to this one, we need to write it and put it above. So we're going to say define a function to choose. Let me just look at this student message a second. Okay, so define a function to remove the host's choice, or to work out. Effectively, we need to think about the way this works. So let's write this down here. Let me just get rid of the code for a second. So if our door choices are random array, let's just say we've got door 1, 3, 2, 1, 3, 2, 1. This is player choice. This means the player has chosen door 1, door 3, door 2, door 1, door 3, door 2, door 1. And let's say the win is 3, 2, 1, 1, 2, 2, and 3. Okay, so those are the. This is the winning door, which the host knows, and then we've got this other thing that we need to choose, which is the host choice. So looking at this one here, the player has chosen door number 1, so the host could remove 2 or 3, and it could open that door and show there's a goat behind it. It's not going to open door number 3 because it knows there's a car behind it, so it has to be door number 2. Okay, so this choice for this one here, the choices the door can open are 2 or 1, and it knows there's a car behind door number 2, so it's not going to open that, so it's going to open door number 1. So we need to come up with this logic to go through. We can see very similarly here that the door this one's going to open is going to be 3. This can open either 2 or 3. It doesn't matter because the player's chosen the winning door. This one here, the door that's got to be opened has got to be door number 1. This one here, the door that's got to be opened is going to be either 1 or 3. And then this one here, the door that's got to be opened is door number 2. So we need to do some little bit of logic to think about how to get this to work, and I'll try and narrate this as I'm going through it. So let's remove that, put this back up. So there might be a way to do this with some smart indexing, but the way that I did this when I wrote it was just to iterate through this array, and it was still pretty fast for our purposes. So I'm going to use that same sort of method here. So we're going to define a function to choose a door that the host removes. It can be either of the doors that the player has not chosen and should not be the winning door if this is in the let's do this here. Def So what I'm going to do here is whatever the value of that verbose flag that's been set down here, that's going to be passed into this host removes as well, and it's going to go in here into this new function which is called host choice. So if we now run this code, it doesn't like it. Because I haven't put anything in here. So if you write a subfunction and you've sort of set it up as a if you set a function up and you haven't put anything in there yet, it's expecting an indentation block. So if you haven't got anything to write in there and it's just a placeholder, you can write pass. And then I write that and it doesn't like this because I've asked it to pass. It says down here, name winning choice is not defined. It's because I've asked it to put this winning choice object in here and it doesn't have that. It has one called winning door. So let's call it there. And if I run this again, here we go. So let's do a clear over here. And we'll just run this again just to show this code now works. It hasn't done anything because nothing in here actually does anything yet. So we need to think about how to get this choose host door to work. And what we're going to find is that it would be useful to just have a list of those doors quite often. So we're going to make up at the very top that's available to everything. We're going to say all doors is an NP array of doors 1, 2, and 3. Because that is going to be useful for us later. Okay, so we've got that here. Run this, doesn't work, doesn't do anything again. Oh, it's because I've removed the pass block, but that's okay because we're going to keep running through this. So what do I need to do in here? So I am going to go through each one of those doors and we're going to iterate through them. So we're going to iterate and just check each one. So I'm going to say for the player choice and the winner in a zip object containing both player and winner. What I'm then going to do is I'm just going to print to screen each of those choices. I'll say I'm going to do something a little bit complicated here. So I'm going to say for I, comma, p, comma W in enumerates the zip object of this. And this is going to be a little bit complicated syntax, but you'll see what it means. Because we can then say if verbose print in round I player chose door P and the winner is W. So if we run this, there we go. In fact, let's just do I+1 because this gets rid of our Python indexing. Okay, so this is now printed out those choices. In round 1, player chose door 1 and the winner is 2, so we didn't win. We haven't won yet. In round 2, player chose door 2 and the winner is 2. So what we can do here is we can, again, this is only printing it out because it's verbose, but we can see this is pretty quick, even for say 1,000 cases. We run this, it runs through pretty quickly, okay, because we're not doing anything super complicated. For 100,000, it takes a little bit longer to run through, but most of the time it's taking to do this work here is actually printing to screen. So anything that you print to screen using a verbose flag like that takes a little bit of time, which is why it's useful to have these things to print to screen when we're testing code. But it's also useful to be able to remove them, because let's see how many times this is running like this. This is taking a long time. This is taking more time than I would want this code to work. So now this is done 100,000 times. Let's just change this flag to false down here. And hopefully if we try and run this now, let's do this again, let's run it. Let's run that quickly, okay? So it runs quickly. It's still gone through and done those 100,000 times, but just because it's not printing to screen, it's no longer taking so much time. So it's why it's useful to have that sort of verbose flag, and we'll do 10 games here, because I can easily then just check the logic of my code. So that verbose flag enables me to print things to screen and remove them all very quickly in one go. So we're going to go through here. So I'm just going to, let's put some narration in this code. So we'll say, so how did I do this last time? There's a couple of different ways we can do this. I'll put them both in here as well. There's a myriad of ways you can do this. I did some quite fancy Boolean indexing, but let's do what you'd think to maybe do as an undergraduate. Let's say, so this host choice, we're sort of thinking in the mindset of the host. So we'll make, there's two choices basically. Either the person has chosen the winning door, or the person hasn't, okay? So let's do the very first thing, work out which doors we can open as the host. So this will be anything in this all doors array that isn't the player choice. So we'll say can open is equal to all doors where all doors is, I forget, not equal in Python, not equal. I've forgotten the symbol for not equal. So if A is equal to 1, B is equal to 2, A, there we go. Because I switched between programming languages, I forget. So the symbol for not equal is an asterisk. Sorry, not an asterisk, an exclamation point and an equal sign. So I want, over here, I want the doors that I can open is equal to all doors where all doors is not equal to the player choice, which, because we're going through this iteration for this round that's equal to p. So let's say if verbose, let's move this line down here. In round 1, player chose door P and the winner is W, so the host can open. There we go. So we've got in round 1, player chose door 3 and the winner is 3, so the host can open 1 or 2. In round 2, the player chose 3 and the winner is 1, so the host can open 1 or 2. These are all just based on what the player choice is. So let's just check all of these. Player's chosen door 2, so we can open 1 or 3. Yeah, these all work. This is not particularly instructive the way this line works here, so we're going to change the grammar in here. In round I plus 1, the player chose door P, so the host can open those two things. New line. But the winner is W. Let's just see if that works. Let's remove these indents from here. But the winner is W. And then I'm going to put another new line in here. That's just a / and an N. And we're going to change this. We'll say can open. Just making this read more like a sentence. If we call it verbose, it should at least make sense. Okay, in round, so there we go. So in round 1, player chose a door 3, so the host can open 1 or 2. But the winner is 1. So this then is going to dictate the rest of the logic flow of our problem. So we're up here. Okay, so those are the doors the host can open. So we now want to, if the winner happens to be in that can open array, we're then going to remove it. So we're then going to say, because the host doesn't want to open the winning door. The host only ever wants to open that door with the goat behind it. So we'll say remove the winning door from the doors that could be open. So we're going to say we'll call this smart open is equal to can open where can open is not equal to the winner. So now if I run this should say, here we go. So let's have a look at the way this works. So this first choice here, so in round 1 the player chose door 3. So the host can open 1 or 2, but the winner is 1, so they can only open doors 2. Okay, doesn't make much sense the way it's been written. Let's just go down and look at another choice. So let's write down at the bottom, the player happens to have chosen the winner. So it says the host can open either door in this case. So we've got to do a little bit more logic in the way this works. I'm just going to tidy this sentence up a little bit. Let's make a smart open string is equal to whilst I'm thinking through some of this stuff, I can't always narrate it or talk about it that easily. So we'll say see if this works. So what I've done is I've created a little string that is either going to say door 1 or 2 or door whatever. And I'm just going to replace this into here. So this then let's try running this. There we go. Oh, okay, that's silly. It's because these square parentheses should be inside here. Because what it's doing is it's printing out exactly what I've asked it to do. These parentheses are saying, I only want this bit to be in here. And because this is still an array, I even want to get it to get the last one. So where it's saying like here, where even though there's only one choice in here because it's reached this line, it's still giving me brackets around it because I haven't told it to take the first item out of here. Okay. Cool. Okay, so there's this still, and just because I'm being very anally retentive, this whole logic doesn't make all that much sense. It says in round 1, player chose toward door 2, so the host can open 1 or 3. But the winner is 1, so they can only open door 3. That makes sense. This doesn't make a lot of sense grammatically. In round 4, the player chose door 1, so the host can open door 2 or 3. But the winner is 1, so they can only open door 2 or 3. So let's just make a new string to go in here. Let's say like a string which is called grammar nitpicking. If there is a 2 doors, we'll say and let's just say, let's replace this little bit here where it said only open before. We're going to replace that with grammar nitpicking. There we go. So this now works to explain how each of these choices goes. So the bit that we want to return is the smart open array for this. So what we've done in this part here, this is determined the door the host is going to open for each one of these individual games. So we need to actually remember that we're calling this from a big large game. So down here we set this up as 10 games, and then we've put all of those 10 choices into this line here, host removes, and we've gone into here and it's iterated through one by one. So what we want to do is we want to add each of those to one big array. So I'm going to put these into a list, which is called host choice is now an empty list. And then what we want to do down here, once we've picked that only one the host can remove, we want to put it into that array. So we'll just say, and we're still within this loop here. Let's just check we're still within that loop. Yeah. Something funny going on with me indenting here. So I'm going to say host choice.append. I'm going to put something into it, and the one that I'm going to put in is smart open. Oh, there's something else we haven't done yet. We haven't chosen a random door between those two. So I should put this in here. Let's put this in here. So we just run this code again. And again, you're having to deal with me thinking about how this works. So in these cases, it hasn't chosen which door to open because got to choose a random one between those two. So I could just always choose it to pick the first one or the second one, but that's sort of lazy. We want it to be truly random. So we're going to say that our random choice is equal to, and we need to choose a random part of this smart open. So we'll say smart open, and then this just needs to be an integer that's either 0 or 1. So we'll say I could import random, but I've already got mp.random.randint. So we'll say mp.random.randint. The maximum it could be is 1, so we're going to say it's 2, and its size is equal to 1. Let's check that works. That seems to work, that's fine. So then let's move this smart open string down here. What I'm doing will make sense. So this then is there we go. So now what this code does is it went in those cases where there's been random choices. So here it had door 2 or 3, which could be chosen. Door 2 was randomly chosen. We have door 1 or 3. Door 3 was randomly chosen. So what I now need to do, one last thing, is just let's make smart open let's call this host choice. So we'll say the this choice is equal to random choice. And then if we're down in this one where I only have one option, then we'll say that this choice is equal to smart open naught. I don't necessarily need to do this line, but I'm just trying to be, there we go. So now, once we've gone through and we've done all this printing, what I want to do is add this to that host choice vector. So we'll say host choice.append, and then we're going to put this choice, which is that single choice at the end of it. If I run this, it doesn't like this indentation. Yeah, let's leave that here, and now we're going to put that there. There we go. So this is now iterated through all of these, and it's appended this thing into host choice. So now what we can do is we can just say, once we're done with all of these, return host choice. So this has now defined our entire function that does all of the choosing on the host's behalf, and this has then become the host's removes. So this is the one, and it's a list of doors that the host removes each time. So let's go down here, and we're going to do print. We'll say if verbose print that's an issue. Okay, so 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 what it said here, this would still work, but I'd rather get rid of this. So every time it's picked a random door, it's left this as an array, and I can see it's when it's picked the random doors because it's game 2, game 3 here, and it's chosen a random bit. So up here, this random choice, I can just choose to take the only item out of there. There we go. So we've got this now. What we can now do is we know this bit works in here. This bit of logic was it only in here to help me work it. So I'm going to now say host removes, and then when we run this host removes part, I'm going to say verbose is equal to false. So if we now run this code, there we go. It now says player choices are this, the randomly selected winning door is this, the host removes those ones. So now we can get the idea whether the player wants to switch or not. So we've got to the point where player chosen a door, the win has been chosen, and the host has then removed a door that makes sense. It's either removed in no case has it removed a winning door, basically, and it's removed one that is also not the player choice. So we've got this far, which is pretty cool, and now what we want to do is we want to make some logic that returns the door that the person can switch to, basically. So we'll say so then this is going to be a function of the original choice and of the door the host has just removed. So we'll say switch door is equal to player switches, and it's going to be a function, like we say, of the player choice, and then that new array that we just made called host removes. So this is then, if we try and run this again, it's not going to like it because player switches hasn't been defined. So we'll go down here and we'll make a new subfunction called def player switches, and then it's going to be player host verbose equals false. And we're going to make this verbose. This might be a little bit confusing. If I just apply verbose here without equals anything, it's applying the value of the variable verbose, which happens to be going into this thing called verbose. If I give it a keyword and an argument after it, then this tells it to input the value of verbose in this one up here and give it value false. So this might be a little bit confusing, but it's the way that I like to write code because it just helps me quickly change things around. So if I run this now, it'll work, and even though it's got the default value being false, it's choosing the value which was input into this master program, which has been set by the Monty Hall flag down here. So let me think about what we need to do in this sort of player switching. So the inputs here are the player choices and the door the host has removed. The outputs needs to be the door that is not either of those. So we're going to do the same thing. We're going to iterate through. I'm just going to copy this line down here. Remove this past. And instead of P in player and winner, we're going to put player and host. And again, I'm just going to put a verbose flag that just does a bit of, not a verbose flag, I'll put a statement that prints this out. So let's say print, and let's say if verbose, print, and we're going to make an F string. In round I, the player chose P and the host removed H. I doesn't like that because I've got an extra curly bracket in there. There we go. So this is just, again, these lines are only there to make sure that my logic is working when I'm writing this code. We'll remove this once we're done. What we need to do is we want to create something called the switch door. So we'll say the switch door is equal to this all doors, where all doors is equal to neither P nor H. So we're saying switch door is equal to that all doors array, where all doors is neither equal to the player choice or the one the host has removed. Let's see if that works. No, it doesn't. It shouldn't be that sort of and, it should be an ampersand, that's why. Nope, does not like that. Oh, okay. This is something I had to learn when I was doing this. So let's talk about this. I'm going to comment this line out. So let's look at these two Boolean indexes. So we'll say all doors not equal to P. Print all doors that are not equal to player choice. And I'm going to, well, let's say F. There we go. So the doors that aren't the player choice are false, true, and true. So it says, here we go. So the player, yeah, let's just move this down here. Put this in here. So this is only really temporary, this line, just to explain this bit. So we'll say, okay, so in round 0, the player chose 3 and the host removed 2. So the doors that aren't the player choice are either doors 1 or 2. So it's true, true, false. And then if I do a similar line here, the doors that aren't the host's removal. I realise I've misspelled aren't, but it doesn't matter for now. We'll say that's where all doors are not equal to H. So what we want to do is we want to have the only door the person can switch to between these two. So it's the only place where both of these equal true. So because these are two Boolean arrays, I can't just, because I can't, unless someone can correct me on how I do this, I couldn't find a way to easily make these equal to each other. What I would like an array that gives me false, false, true for this. And if I just try and make these equal to each other, or if I try and do a logical and, let's see if we can get this to work. We'll say, well, this is what I tried to do here. We'll say combining these Boolean arrays, or trying to combine them and say is all doors equal to H. Let's say all doors is equal to P, and it doesn't like that. And let's try doing it this sort of and. Doesn't like that either, because and I've never found a way to get around this error other than this way. So what I'm going to do is I'm going to make I want to do something called Numpy logical underscore and. So we'll say player removal, sorry, player switch is equal to the numpy logical and and then we need to put both of those Boolean indices into here. So we want the case where both that is true, comma, and this is true. Well, that doesn't work because I've copied the wrong parentheses in there, so let's just check here. There we go. And so let's just make a new line down here. We'll say the door that the player can switch to is here we go. So let's just go back over this top one. So what we want this to be printing is, the first one is the player choice. So the doors that aren't the player choice are door 2 or 3. The doors that aren't the host removal are door 1 or 2. So the only door the player can switch to is door number 2. So in each case, we want this third line to be the combination of where both the top ones are true. So here we go. This one is true where these two are true. This one is true where these two are true. So this is a little bit annoying to have to do. But what I've now got is I've got this line here, player switch is now the line that gets this for me. And the reason I'm showing this is just, the reason I'm showing this is because you need it to solve this problem, but this is a way that you could just print things out using a little bit of logic to solve a problem. I had to do a bit of Googling to get that to work when I got it to work, but now we've got it. So this says the player switch. Now what I can then do is I can then make this, because this is now just a Boolean array, I can then choose all doors of that. I run this then the host removed H, so there we go. Host should switch to this. And now what I want to do, so just check this works. The player chose 3 and the host removed 2, so the player should switch to 1. Good. The player chose 3 and the host removed 1, so the player should switch to 2. Now this makes sense. It's got these square brackets around them. So again, I could either choose to just print out the last element here. So I could do 0 here. But instead of doing that, I'm going to put the 0 up here. Just tell it that whenever it makes this player switch to only get the integer that comes out of here. There we go. So we've now got our array of the player switch. I'll do the same thing again, which is we'll say we'll call this the switch array, and then we'll do switch array dot append player switch. And then we'll do return switch array. I haven't set this to be equal to an empty. Yes, I should do. So this is now set up this switch array, and it's going to return an array. It's actually a list, but it's returning a list of the doors the player can switch to each time. So if I go down here now in my main bit of code, I can do if verbose print player should switch to switch door. If I run this, it's still printing out all of these intermediate steps. So again, I'm going to go back up here. I know this bit of logic works now, so I'm going to set this verbose flag equal to false here. Okay, so the player, here we go, setting up, let's just do a clear again, and we'll run this again so I know which version we're looking at. So if we run this piece of code now, setting up 10 games in the Monty Hall Problem. Player choices are, let's look at this first game, 3. The randomly selected winning door is 3, so the player actually chose the right one this time. The host removed door number 1, so the player should switch to 2. In this case, they didn't win. Player choices here are 1. The randomly selected winning door is 2. The host removes 3, so the player should switch to 2. So we now want to see in which case the player wins. So we don't need to make subfunctions for this. We didn't need to make subfunctions for any of this. It's just the way that I happen to set up the code. So we're now going to work out logical arrays of where the player won and where the player would win if they didn't switch. So we'll say the win original, it's going to be a Boolean array, and it's going to be wherever the original player choice is equal to the winning door. And we'll say win switch is equal to switch door is equal to winning door. I'll do if verbose, print and I'm going to print these two Boolean arrays out. There we go. So, yeah, okay, let's just check the logic if this actually works. So the player choices are 3. The randomly selected door is 3, which is true. So if they won in the original case there, and they would have not won if they'd switched. Okay, second game, player chose 3, winning door is 1. So they didn't win in the original choice, but they would have won if they switched. So we've got those. Again, this is game 1, game 2, game 3, game 4, game 5. So what we can see, we can look at the percentage of where we win in these cases. So we can just count them. So we can say there's 2 ways we can do this, and I'll show you one or 2 ways, but I'll show you my logic of thinking through this. So determine the win statistics. So we can say that the original wins is equal to the sum of win original, and because it's a Boolean, it will count it as a 1 if it's a true, and it's a 0 if it's false. So I'm going to say this is going to print out the percentage of games won with the original choice, and then the percentage of games won with the switched choice. Okay, so for 10 games, you win with these 10 random choices. They're taking the bins out, it's incredibly noisy. There we go. So the numbers dance around 40. And if we take this up to 1,000 games, these numbers are much closer to the percentages that we were expecting to see. Let's just turn this to an integer. No, let's not. Let's have a bit decimal with 1 decimal place. So that's done that. What we want to do is I'm still going to keep this verbose actually, but let's think about what I did with the original code. So what happened with the original code is we were able to plot the number of wins with increasing games, and at the moment this can only look at the number. It can only look at the ending number of each of these. So what we can do is we can do the cumulative sum of each of these. So we can, if we've got an array that's 1, 0, printing. Oh, it's not on screen. Let's put this up. And my iPad is not on screen. Excellent. Okay, I'm not gonna get fanning around getting my iPad working. So the cumulative sum, rather what we've done is the sum for everything. So the cumulative sum is the sum up to that point of an array. So let's just say if we've got a is equal to range 10. Let's do np.arange10. Oh, didn't mean to do that. If that's my array 0, 1, 2, 3, I can do print np.cumulative sum cum sum, no giggles. There we go. So it now does the cumulative sum. So the first element is the sum to that point, which is 0. The next one is the sum of the first two, 0 and 1. Then it's 0, 1, 2 added together, 0, 1, 2, 3. Here we go. So you can see how this works now. Okay, so that's what the cumulative sum is for, and that's going to enable us to work out the percentage of wins up to any points. And this is the step that's a little bit smarter, I think, in the way that I've approached this than the version I saw, because I'm trying to solve a different problem. I want to plot the number of successive wins. So rather than running n number of games successively, this just means I can run that number of games once and then do the cumulative sum up to that point. So we'll say cum sum original is equal to, let's just change, I'm dancing around a little bit here, so we'll say with what I'm going to do is remove these from the verbose because I always want to print these two. We're then going to determine the cumulative sum is equal to np.cumsum Now what I can do is I can plot out an array that just goes from 0 up to almost the number of games, and then that will tell us the amount that's been done. So we'll say, in fact, let's just make, so if we run this, what I've now got is this cum sum original and cum sum switch, which are the two cumulative sums up to that point, which is then the percentage chances that I can plot over the increasing games. So I don't have a vector of the number of games, so let's just make that. Let's do n games is equal to np.arange n. Just remember that in Python, this for 1,000 games it goes up to 99, starts at 0. So rather than messing around with the syntax in arrange, we're just going to add 1 to that. And now what I can do is I can make two plots that give me the chances. say plt.figure. Firstly, let's do plt.close, because otherwise this is going to make a bunch of figures and they'll keep clogging up system memory. So we'll do plt.close all, plt.figure, and then we'll do plt.plot, and I'm going to do endgames, sum original, and then I am going to say a label is equal to, and just give it a name for it, so the label is going to be equal to didn't switch. Run this. X and Y must have same first dimension but have shapes 1001. Why doesn't that work? Let me have a look at what that sum original. Oh, that's why, because I've put the wrong thing into here. So this original wins is just a scalar. So I should have put this. These should have been win originals and win switch here. That's why this will now work. There we go. So that is. That's not right. What is this doing? So let's just print this out. I'm going to reduce the number of games, try and figure out what I'm doing, try and not get too infuriated with the guys throwing their recycling out the windows. Oh, okay. That's why, because I need to, the cumulative sum at that point, I've just added up the number of wins and I haven't divided it by, I need to divide it by this n games up to that point, because let's print this out, cumulative, so I'm printing out this, print these both out. So this then is the cumulative number of games won to that point. So this says that if you switch, you get 7 games won by 7 out of 10 games won, 3 out of 10 games won with the original. So at the moment, this isn't a percentage; these are just numbers. So what I need to do is I'm going to put this vector of the number of games above here because I need to divide it by that number, and then we're going to turn it into a percentage. So divide by n games times 100. If I run this now, it should, there we go. So this is the original. Let's do plt.legend. And we'll put the other plot on as well. There we go. So this is what we're showing here. Let me just do plt x label. We're going to label the plot. So along the x-axis, we've got the number of games played, and then the y-axis is the cumulative win percentage. So plt.title. Okay, so we're now going to plot this out. Here we go, cumulative win percentage for n games of the Monty Hall Problem. That's not an F string, that's why that didn't work. So again, it doesn't show very much for 10 games. Let's run this again. 10 games. It sort of shows similar sort of behavior, but sometimes it's wildly different. And I think if we run this just by chance, sometimes you might get that you'll get not switching gives you a greater win percentage. So this is where we take this up to 100, for example. Okay, after 100 games, this number is much closer to 60, 66. Let's run 10,000. Okay, number gets much closer to 66, and not switching keeps you much lower. 100,000 takes a little bit longer. And what we can do now, it's still printing all of this nonsense to screen. So it's not nonsense, but it's stuff that we don't need. Let's just change this to false. We'll run this again. There we go. So we've now produced this. And if I be brave and run this as a million, we'll see how long this takes to run. Might take up to a minute to run, I'm guessing. I haven't done an analysis on how this piece of code works, but I think it probably maybe doesn't increase quite linearly with the number of games, the length of time it takes to run. So just be careful with things like this. Sometimes some problems scale with the number of increased inputs you've got, some problems don't. Oh, there we go, after a million. So let's just run a million games with the Monty Hall problem. That's pretty cool, and we find this number is 2/3. This number down here is 1/3. So that was my rewriting of effectively the piece of code that I gave out to you guys. I've gone through it in a slightly different fashion, and it's the way that a lot of this stuff works is there are many different ways to solve problems, but the logic, it's about how you think about how the problem works and about how you think about solving it. So there's a lot of stuff in here. This is quite a complicated little problem to have solved. Hopefully you guys can follow along and see what we've done here. Like I say, I wouldn't expect you guys to be able to solve this problem on your own. But I would sort of expect you to at least be able to follow along and sort of see what we're doing and having an appreciation for what each of these steps does if you're still a little bit confused by the whole thing. But like I say, this is the end of the course, or the end of semester. We're going to have one more lecture next week maybe. I need someone to provide me with a good problem to try and solve. But that's quite a difficult task we've just gone through. So hopefully that's elucidated what that code I wrote originally did. And if you've learned only one thing from this, it's about putting those little logical flags that enable you to quickly test sort of the logic of your subfunctions by putting a flag in there saying whether things are true or not. So this has just helped me to test my logic in this code. So even if you don't find this problem particularly exciting, the way that I've gone through and sort of spoken about what I'm thinking about, how I'm testing these subfunctions, how I'm using this flag to choose when I'm printing to screen and when I'm not, that sort of stuff should help you in writing your future code. So I'm going to get this lecture up and I'm going to rip it, upload it, and it should be on there just in time for you guys this evening. Look forward to seeing you guys on Wednesday, and I hope you all have a wonderful week. Take care.